Okay, let's do some harder L'Hopital problems. Kind of throw some out there. So let's look at the limit of 1 plus 2x all to the cosecant x as x goes to 0. Okay, so for that x go to 0, remember cosecant is 1 over sine. Sine is 0, so then cosecant would be like 1 over 0, so that'd be infinity. And this would be 1 to the infinite power. So that's the indeterminate form we're kind of working with here. And again, our goal with L'Hopital is to turn everything into 0 over 0 or infinity over infinity, and then we can go ahead and take the derivative of top and bottom and look at the new limit. So what we're going to do here is we're going to apply a logarithm. Okay? And so now we're actually going to find the limit of a logarithm, and then we can exponentiate at the end. That allows me to bring that power down, and since that's a cosecant in front, then this is the same thing. Cosecant in front is the same thing as a sine in the denominator. Okay, so now if I look at the limit and I look at x goes to 0, this is the natural log of 1, which is 0, over sine of 0, which is 0, and now I have 0 over 0. Cool, I have one of these cases, right? I've turned the original 1 to the infinity indeterminate form into this form, and then I can do L'Hopital's. Okay, so now I can look at the limit of the derivative of this. The derivative of this is 1 over 1 plus 2x times 2, and the derivative of the denominator is cosine x, and I can look at that limit as x goes to 0. Okay, and when x goes to 0 here, I get 0, I get 1, I get 2 over 1, and I get 2. Okay, and then I have to remind myself that I found the natural log of the limit, and so then the real limit then is e squared. Okay, so we can do questions like that. How about we look at the limit of e to the x minus 1 over 2x, something like that. And now let's let x go to 0. Okay, and this is a 0 over 0, and so when we have 0 over 0, we kind of almost immediately just go to L'Hopital's. And when we do L'Hopital's, we take the derivative of the top, which is e to the x, the derivative of the bottom, which is 2, and then we apply the limit as x goes to 0, and we get half. Okay, so that one was an easy one. Okay, how about we look at the limit of x times the natural log of x as x approaches 0 from the positive side. So this is a right-handed limit. And what we have here is that this is, remember, the natural log of 0 is negative infinity, and this is 0. So this is 0 times infinity. You're like, oh, I don't know what that is. Well, this is what L'Hopital does. This is kind of an algebra trick. So this is kind of 0 times negative infinity. We're going to flip that down, so I'm not actually going to do any calculus yet. So this is the natural log over 1 over x. So multiplying by x and dividing by 1 over x is the same thing. So instead of 0 times infinity, now I have negative infinity over infinity. So now I have something that looks like that. And now I can do L'Hopital's. So I'll switch to the red pen, do L'Hopital's. L'Hopital says I can look at the same limit. The limit is x goes to 0 plus, but I can look at the derivative of this, which is 1 over x, and the derivative of that, which is negative 1 over x squared. I can do some algebra here and flip that up in the numerator, so it's negative x squared over x, which is equal to negative x, and then I can apply the limit. Again, going from here to here is me doing L'Hopital's. Going from here to here is just doing algebra, and now I can look at the limit. The limit is x goes to 0 of negative x is in fact just 0. So we know that in this particular case that we get 0. So in this particular case of 0 times negative infinity, we actually do in fact get 0. Okay, and there's lots of things kind of like this trick. Here's another one where you're going to look at the limit as x goes to infinity of, let's say, 2x times sine of 1 over x. Okay, so this is infinity times sine of 1 over infinity. So sine over 1 over infinity is 0, right? Because 1 over infinity is 0. Sine of 0 is 0. And then this is infinity. So you're like, oh man, this is infinity times 0. It's another kind of infinity times 0 case. So let's leave that 2 right where it is, and let's move that x in the denominator. And again, this is not doing any L'Hopital's yet. This is just me rearranging 2 times sine of 1 over x all over 1 over x. Okay, and now I can look at it. So now when I let x go to infinity, this is 0 over 0. And you're like, okay, cool. Once it's 0 over 0, then I know I can do L'Hopital's, and I can look at the limit as x goes to infinity of the derivative of this. So that 2 just chills. And the derivative of sine is cosine of 1 over x times the derivative of 1 over x, right? Chain rule, negative 1 over x squared, all over the derivative of that, which is negative 1 over x squared. Hopefully you can see that these conveniently do cancel. And now let's look at the limit. The limit is x goes to infinity. This is cosine of 1 over infinity. That's cosine of 0, which is 1. And I get 2 times 1, and I just get 2. So this limit is equal to 2. So in this particular case, this limit was 0, and this limit was a half. So those are our 4 examples. In this case, infinity times 0 was 2. Over here, infinity times 0 was 0. You just don't know because you have to go through the process, because all of these indeterminate forms, 0 over 0, infinity over infinity, 0 times infinity, infinity minus infinity, all of these cases, they're just different, and you're not really sure what they exactly are until you actually go through the algebra and figure them out. Okay? So most of the time, if you have 0 times infinity, you're going to take this x and you're going to flip it down and make it 1 over x in the denominator. Both of these cases kind of use that same trick. If you already have 0 over 0, then you jump right to L'Hopital's. If you have some exponential, you're almost always going to apply a logarithm, change the exponential to a product, and then once it's here, you either do this trick, or in this case, this was cosecant, and easily flip down to be sine. So 1 to the infinity, 0 times infinity are kind of these tricks, and these are the more popular ones. If it's already 0 over 0 or infinity over infinity, then you can just apply L'Hopital from the get-go. And then there's at least one more case that I wanted to look at, where you're looking at infinity minus infinity, because that's usually 2 separate fractions. So let's look at this guy. And this one is a little complicated, which is why I want to show it here. So let's look at the limit as x goes to 1 from the positive side of 1 over the natural log of x minus 1 over x minus 1. Okay, so this one is a little dicey, and again, it's a right-handed limit because I don't want to look at the natural log on the other side of 1, so I'm looking kind of at a 0 plus. So this is slightly bigger. The natural log of 1 is 0, so going from the right side makes it 0 plus. So this is 1 over 0 plus, so this is infinity, minus 1 over something bigger than 1 minus 1 is 0 plus. So this is infinity minus infinity. So if you have infinity minus infinity, you're like, oh my gosh, I have no idea. Which version of infinity is bigger? I don't know. Well, L'Hopital, again, satisfies this. But to do L'Hopital's, we have to get infinity minus infinity to make it look like 0 over 0 or infinity over infinity. So we have to make it a fraction. So, I mean, I think it's pretty obvious at this point that if you need to make it 0 over 0 or infinity over infinity, because you need it to look like the limit of f of x over g of x, right, as x goes to, in this particular case, some a, well, then you have to make it a fraction. So make this a fraction, right? So exponentials, we apply logarithms. In this case, we have 2 different things. We got to multiply top and bottom. So I'm going to multiply top and bottom here by x minus 1. I'm going to multiply top and bottom here by the natural log. So it does get a little messy, but I get x minus 1 minus the natural log of x all over the denominator is x minus 1 times the natural log of x. And again, I'm still looking at the limit as x goes to 1 plus. Okay, let's see what I've actually changed this to now. So now, when I plug in 1, I get 0 minus 0, which is 0, and I get 0 times 0, which is 0. And you're like, oh, cool, check it out. I changed infinity minus infinity, indeterminate form, into 0 over 0 by just adding and subtracting fractions. Well, now I have a fraction over a fraction. Now I can do L'Hopital's. Okay, so now we can do L'Hopital. So I'll change the red, and this is me taking the derivative of the top and the bottom, which is what L'Hopital allows us to do. The derivative of x is 1. The derivative of 1 is just goes away, and the derivative of the natural log is 1 over x. Okay, all over the derivative of this. You're like, oh man, this is a product. Okay, so we have to do product rule. So this is x minus 1 times this, which is x minus 1, times the derivative of the natural log, which is 1 over x, plus the natural log of x times the derivative of that. Okay, so now let's check this out. What do we have here then? And you're like, okay, so this is 1 minus 1 over 1, which is 0. And then this is 1 minus 1, which is 0 over 1, which is 0, plus the natural log of 1, which is 0, and you get 0 over 0, and you're like, oh man, I get 0 over 0. Well, sorry, but you're going to have to do L'Hopital's again. There's really nothing else you can do. So let's do L'Hopital's again, because we still have an indeterminate form. Let's continue to work with this. And take the derivative of the top, which is a negative, oops, sorry, the derivative of the top is actually going to be a positive 1 over x squared, right? The negative and the negative are going to cancel. All over, and let's think about what this can be first. Let's rewrite this. So I don't want to do quotient rule. That's really just a 1 minus a 1 over x, right? This is just x over x minus 1 over x. Let's look at it like that. It's going to make it easier. So then the derivative of the 1 goes away, and the derivative of that is 1 over x squared, and then that is plus 1 over x. Okay, let's do some algebra here. Before we try to plug in here, let's do some algebra. So again, I'm not going to do another L'Hopital's. I'm going to say equals, because I'm doing algebra. I'm going to multiply everything by x squared. Okay, I'm going to multiply the top by x squared. I'm going to multiply the denominator by x squared. So then x squared over x squared is 1. X squared over x squared is another 1. And then x squared times 1 over x is just x. And look how nice and easy this is. Now let's plug in the limit as x goes to 1, and I get 1/2. And I'm done. Again, this one is a pretty complicated one. I'm going to end you with this one. But if you have infinity minus infinity, that means you have two different things. Well, those two different things you're going to combine to one fraction. Once it's one fraction, then you've likely turned infinity minus infinity into 0 over 0. This was a little complicated because we ended up having to do L'Hopital's twice. We got 0 over 0, we did L'Hopital's, and we still had 0 over 0. So we did L'Hopital's again, and then I did a little algebra manipulation here to change it to this, and then I just applied the limit as x goes to 1, and I get 1/2. And again, if you look through all of the L'Hopital cases, these two are the most popular. The AP test does love 1 to the infinity case. They do love that, and they also love 0 to infinity. Both of those examples, I did on the front, and then this was an example of infinity minus infinity. Obviously, there are a couple other cases that I didn't show, but they're all very similar. Again, hopefully this helps you with some of the more difficult L'Hopital questions.